Hi, welcome back. And so last time we did this kind of deep dive into turbulence and actually really boundary layers, some internal and external flows, and really what you're kind of seeing at this stage of the point in this undergraduate fluid mechanics is sort of this foundational layer. And then what I'm trying to provide on top of the foundational layer here that you may miss in the book is actually then pointing to why this is still really, really hard. And so pointing towards whether that's an advanced, graduate course, which we're going to do here as I get into sort of graduate fluid mechanics, or ultimately getting into, very industry specific things like flows over an airfoil. Or later in this book club, like I'll probably come back and do some rocket engine stuff and some jet engine stuff. And so there's all of these pieces that all of this is kind of pointing towards from these disciplines that are ultimately pretty challenging, and but still exciting because we actually are, again, we're trying to build like real things like real cars and boats and submarines and aircraft and spacecraft and all the stuff, launch vehicles. So this is really just sort of that foundational layer. And here, and these sort of next two chapters, where I'm going to try and add some flavor again is that in that context, this is now compressible flow. And so all you might see in the basics of an undergrad fluid is just, again, maybe sort of deriving a couple of these equations, little teasers, and I'll try to do my best here to sort of point to it. But this will be absolutely very critical when we go back to things like applications, whether it's rocket engines, jet engines. And if you've already watched my first book club on accoutrement, which is sort of advanced, aircraft design, which includes, subsonic, which at some point, subsonic stuff, you have to have that compressibility. And then ultimately, why I love that accoutrement book is it gets into high-speed flows, aircraft. So, Mach 2, Mach 4, where kind of Venus is trying to play. So this basics in compressibility is super important. And what we're going to do here, in sort of just a definition, is imagine there is a shock. This is a discontinuity where beforehand I had air. Again, water would be incompressible, so this isn't going to work. So let's think of air, but truly it can be any gases. But air for our context will work. And the air has some velocity, which we're actually going to specify as the speed of sound. We're going to derive what that is. But there's some speed that'll be very important, so we'll label it C, that this air is traveling, and some pressure, such that on the other side of this, we have a change in density, we have a change in the velocity, in decrement, and we have some sort of change in pressure. Now, really, this air, you can think of it as a sort of coming at, maybe there's some object over here, and that's what's creating the shock, as a sort of standoff from an object. That's okay. That's one way to think of it. That's why we're going to sort of frame this as the air was, we'll say sort of supersonic way out there, and then it's slowing down, like on a stagnation point. It's slowing down, and then it hits this magical velocity where a shock then occurs, and then past that, it is now subsonic. So that's what I'll have you sort of frame in your mind. And so when we come and really back to the earlier days of what we did in fluid mechanics, if we sort of look at this from a controlled volume point of view, just around that, we can then do conservation of mass. And so again, because the flow is coming in this direction, this one will pick up a minus rho C, and I'll just use A generically to refer to the area of whatever this cross section is of this box, sort of the face of it. So that way that's mass. And then on the other side, there's a density plus whatever that increase in density happened. There's the velocity minus whatever that change in velocity, the delta V, times area. And mass is conserved, so that'll be equal to 0. Okay? And so you'll notice that some of these cancel out, like the rho CA and the rho CA. And so that's gone. So what we're left with is minus d rho dV A. Okay. Sorry. Take this back. Left with minus rho dV A. So the first term, rho minus dV A plus d rho C A is equal to 0. So that's all that was left. And so solving for dV, that's a dV is equal to C over rho d rho. Okay, so that's sort of important equation number 1. So I'll put that boxed in green. Okay, and then coming back and doing the sort of conservation of momentum, I'll go ahead and write that integral as well. And so that's rho u x velocity, and then uj daj is equal to the integral of p minus p dA. Okay, so I left it in this form again to sort of, it's this only x momentum. I've only carried x velocity, and then I've kept this as a vector. Okay, just to remind that, you know, if there was sort of flow escaping what I would frame as the y direction here, you would have to account for it. It's not, and so this is going to simplify down to at least the pressure side. Let's do that first. This is basically on one side or the other, so P times A, and then minus P plus dP times A, which is just minus A dP. Like that, that's it, right? It's just that pressure force is just the area times that change in pressure. Okay, that to be expected. And so then the left-hand side of this, got to track a little bit more. Okay, and so we'll do, the speed is C, okay, minus rho CA, and then plus C minus dV, rho plus d rho, and again C minus dV times A. Right, so you sort of, what you should see here is sort of a pair of velocities and times the area, a pair of velocities times the area, and then the density associated with it. Okay, and so that's equal to minus A dP. All right, so if you go through and sort of do all the cancellations, what you're going to be left with is that dV is equal to 1 over rho C times dP. Okay, so there's step 2. And if you, basically I have 2 forms for dV, and so you put that in together, you're going to have C squared is equal to that dP over d rho. Okay, so that's really the first step, that the speed, that speed of sound squared is sort of that change in pressure over the change of density. And then, you know, let's see if we can figure out what in the world that would mean. So if we go to ideal gas, and again, air can be treated well as an ideal gas, kind of back to what we're doing there in statistical mechanics, there's actually some portions that are real ideal gas that doesn't exist. But however, even though air, you know, just mostly nitrogen, some oxygen, those are all diatomic molecules, we can actually adjust it, and we account for both translational motion as well as the rotation of those diatomic molecules. It's still not too bad to treat it as an ideal gas. It actually just changes the ratio of specific heats. So this is gamma, and for air, it's 1.4. Okay, so that's why I did that portion in thermo, so that this makes a little bit of sense. Okay, and from also thermodynamics, we have that P over rho raised to the gamma is constant. This was an ideal gas adiabatic process. Adiabatic, as in like no heat coming into the system, which is true. This is just a shock. Okay, and so if you do that and you take a look at the derivative, so let's then say, well, what would be dP over d rho? Well, derivative pressure. So put this up here. This is constant raised to the minus gamma. Okay. And what you'll see, that's equal to gamma and then P over rho. And P over rho, if we go back to ideal gas, also definition, this is gamma RT. And so, well, there we go. And so this is then a very easy, if you will, or our standard definition of what is the speed of sound. Well, for an ideal gas, it is the square root of the ratio of specific heats times the gas constant. Again, this is not the universal gas constant, but the actual gas constant, so be careful there, times the temperature. Make sure your units work out. That's a super easy trap. Don't do that in Celsius or Fahrenheit. You're going to get a completely wrong number. It's got to be done in the absolute units and track all of it. Okay, so for air, that speed is roughly 300 meters per second. That's an easy way to remember it. It's one that at least I've kind of committed to memory. It's been helpful for many times. Okay, and I'll link into some derivations I actually did in the Kuchman book club, where I go a little bit more on this. So I've already have kind of some of the video, so I'll insert that link here. And then last little bit, this is sort of a normal shock. What we actually see, if you think through the normal picture that's sort of drawn, is if I have something here radiating, making sound, right? And at some point, sort of peak sound waves doing that. What we have is if this thing is now moving, and so imagine this dot sort of moving with each radiation, and so that's the first level of radiation, that's the second level of radiation. Oh boy, I didn't do that well at all. Okay. Totally jacked that up. All right, starting over. This is going to radiate in 3 different time steps. All right, the one on the far right, because I intended this to move to the right, the one on the far right is the last radiation, so let's say like 1 second. This one radiated for 2 seconds, let's call it that, and then this one radiated for 3 seconds, let's call it that. And try to draw that really close. So what you see is basically the air over here doesn't have a chance, if this is singing or pinging or whatever you want to think of it, sound waves that are traveling don't get the chance to actually do it. So that would be sonic. And then if you draw effectively the same diagram, I'll basically leave it alone, but what you end up happening is that these waves then are actually disconnected, and you get an angle. And the angle, very important, sine of that angle is 1 over the Mach number. And so that's where you get a shock cone. Okay, this is cone radiating away from the thing punching through the air. Okay, so those are some basic relations, and what you'll see in the text and some of the homeworks is basically like some very simple stuff. I have a supersonic aircraft at this Mach number. What's the shape of the cone? Or I'm running an experiment with argon. What's the speed of sound? You'll see some of those things really in kind of the basics of chapter 12, and then the basics then in chapter 13 is what I'll sort of finish with here, just to get to some actually interesting applications. And so what we'll do is imagine you have flow in the system. Generically, this is state 1, this is state 2. And so this is intentionally separate areas. And if you do conservation of mass, rho AV, which is constant, and then you take the derivative of that, what's pretty easy to then do, this is d rho over rho plus dA over A plus dV over V is equal to 0. Okay, so that's just taking the derivative and then dividing through, and you get this. Okay, so normally the way that is then, I'm going to rearrange it and say the area over area is equal to negative d velocity over velocity minus that d rho over rho. Okay. Now let's come back to honestly like more of a Bernoulli. So if you then kind of plug in for Bernoulli, then you're going to see that this is equal to dP over rho v squared minus d rho over rho. I'm switching because my orange is running low. Okay. And now I'm going to hold this outside of the box. I'm going to switch back up to here. So this is coming up here. Okay, so dP over rho v squared. You'll see where I'm going with this here in a second. 1 minus v squared over dP d rho. All right, well, I know what that is. Back to here. That's speed of sound, and that's a minus sign. So that's just dP over rho v squared times 1 minus Mach number squared. Okay. Well, now insert the inviscid assumption. Say inviscid, which is that dP over rho, then the del v squared over 2 is equal to 0. And so you can come back in and solve for dP over rho v squared, okay? And I'll just kind of jump to the punchline, which is then that dV over V is equal to minus dA over A times 1 minus Mach number squared. All right, that's sort of enough math for right now. You can follow along here or follow along in your book. What I'm trying to show you is at least write down the top level stuff. So I have a system going from 1 to 2, the areas are changing, mass is conserved, conservation of mass got us to this point, right here or here, however you want to think of it, and then we inserted the definition of speed of sound to get us to this point, right? And we came back and said, well, what if this is inviscid? As a halfway decent assumption. I know I just talked about like pipe flows and things like that, but if this is a fast-moving air, yes, there's a boundary layer, but this core isn't seeing almost anything to do with that boundary layer if it's happening so fast, okay? So if it's then inviscid, you come along and you get this solution here, which now means this. The change in velocity is equal to negative dA over A. So let's pretend this is subsonic, okay? So this is subsonic. Then this term in the brackets is positive. 1 minus a number less than 1 squared is going to be still less than 1, but it's going to be still positive, which means when you constrict your area, so if the area is going down, then your velocity goes up. You have all experienced this putting your thumb on a hose, like a water hose, right? So when you constrict the area, that flow speeds up. You learn that as a kid, right? Okay, easy. Now let's come back to supersonic, where Mach m is bigger than 1. Well, this whole thing, whatever the term is now negative, and so it switches. That now means when you have, if this portion of the flow, let's come back in this very specific situation where I actually constrict this enough such that I go sonic. Then as this expands, then the flow is actually going to speed up. And so this is then greater than 1. This is the flow gets faster. Okay? This is exactly why rockets are designed with a throat. Okay? And so I have really, really hot stuff here. I am accelerating that hot stuff to a throat, which goes sonic, and then that rocket nozzle keeps going, and I make it supersonic, so I get more exhaust velocity. And that's actually what helps convert all of this heat into momentum by making this go faster. And actually, like I said, I'm excited to sort of next book club kind of get into rocket work, and we'll end up showing how this is actually then the thermal energy is decreasing throughout this whole time, and you're getting more momentum. So this is actually a very simple conversion of heat into momentum using things that go supersonic. Okay, so very, very simple flows. But that's a very basic issue of rocket nozzle, and then that's really the point of this derivation. And what I'm going to leave you with, so just how subsonic flows you understand by putting your thumb over a water hose. You actually already have an idea behind this, and where we need to go to is an analogy of car traffic. Okay, and so when you're driving in traffic, your communication is not instantaneous with the car in front of you. So from a fluid mechanics point of view, instantaneous communication is incompressible. Basically, that the sound waves carry so much faster than the flow, it doesn't matter. You can treat it almost as infinite. And water flow going over, hitting a bridge or hitting a submarine, like it's all subsonic. Okay, that information is propagated upstream infinitesimally, effectively, at infinite speed. In traffic, because you're a human and the person in front of you is a human and the person behind you is a human, there is a delay in communication, just kind of like here, where eventually there's a delay in communication. And so what's happening when things are compressible, you can imagine all of a sudden there's a construction, which is taking your 3-lane highway or 4-lane highway down to 1. What happens? Oh, everybody actually slows down and sort of compresses up. And then when you get through that opening and then it widens back up, what does every single car do? It accelerates away. And so that's actually a very reasonable mental analogy of what's happening in supersonic. Okay, is that if you're supersonic and there's a constriction, if you're supersonic and there's a constriction, you go back to this, actually velocity is going to slow down. And then when the constriction opens up and if you're still supersonic, then it opens up. And it's actually back to this sort of analogy here with traffic. And then my students would often then say, like, well, the ones who are thinking ahead are then saying, well, if communication was instant, what would you actually do? And I'll kind of leave you with this. Well, if communication is instantaneous, maybe there's a world where cars have some sort of network. And so if you have traffic coming up to a construction zone, what you should actually do is speed up, right? So imagine 2 lanes going down to 1. If all the cars actually doubled their velocity and navigated and sort of interlaced well, there would be absolutely no stoppage. So we definitely don't do that as humans, because doubling your velocity is dangerous, right? We know speed kills. And so, this is not going to happen while sort of humans are in control, but that would be the sort of this theoretical thing you could do. Maybe not a pure doubling, but for sure in a world where cars maybe eventually get networked, things like that, you could actually navigate that and sort of things like construction or slowdowns due to whatever in traffic could be navigated by cars that communicate to each other. So you have both models. You have a model for subsonic with your thumb over a hose, and you have this mental model for traffic, which then gives you this idea of why supersonic flows speed up. Okay, we'll see you next time.